Well, there's no question about it. It's been an unusual winter all across west central Ohio and really all across the Midwest and Northeast United States. Definitely not the kind of winter pattern that we've gotten used to if we lived here for several years. And we wanted to take a couple minutes here and talk about why that's been the case, why our weather pattern has been so unusual over the past several weeks and months. And when we look at weather predicting over the course of weeks or months, over the course of the seasons, we are going to be looking at different patterns, different large-scale patterns, oscillations. The most important one is the El Nino Southern Oscillation. And what that is it's a recurring climate pattern. It impacts weather conditions all across the globe. Two phases within this pattern. You've probably heard of them, El Nino and La Nina, and these two phases dictate much of what happens across the United States in terms of our winter weather. They shift back and forth irregularly every 2 to 7 years, and these southern oscillation phases cause predictable shifts in ocean temperatures, and all that impacts wind and rain in the tropics. From there, that causes a ripple effect, which impacts weather pattern all across the globe, including here in the United States and especially here in Ohio. So we want to take a closer look at both of these phases of the El Nino Southern Oscillation. With an El Nino pattern, a couple of things are going on across areas to the south in the South Pacific. Trade winds normally blow east to west, and that pushes warm surface waters towards Asia. But in an El Nino pattern, this isn't what happened this year, but we want to take a look at both oscillations. In an El Nino pattern, what happens is the trade winds weaken, pushing warmer waters off the coasts of South America, and that in turn impacts the jet stream here in the United States. It causes the subtropical jet stream to bring wet conditions to the southern tier of the United States. The polar jet stream is suppressed northward into Canada. In between, in the central and northern U.S., dry and warm weather prevails, and along the east coast, that often means wet weather conditions in an El Nino year. What happened this year, earlier on especially, was we were in a La Nina pattern. That's the opposite oscillation from what we just talked about. And in a La Nina pattern, again here too, normally trade winds blow from east to west, pushing warm surface waters towards Asia. But with the La Nina pattern, trade winds are stronger than usual. That causes cooler water to move to the surface in the East Pacific, and this also impacts the jet stream, but in a different way, meaning dry and warm conditions across the southern United States, an intensified polar jet stream, which often brings wet weather to us here in Ohio, and that did happen this year. January and February above average in terms of temperature, but more importantly, precipitation. That is often the case with the La Nina pattern, and of course, back to the west across California. It's been very wet, lots of snow and rain across California, especially in recent weeks and months. What's happened this year is the La Nina pattern has been breaking down. It's been weaker over the past several weeks, and that's allowed other factors to take place. So again, to recap, the La Nina pattern gradually weakened. A positive North Atlantic oscillation, the NAO, took over our weather over the past several weeks. With this, a persistent pattern that had big impacts on temperature and a lack of snowfall. Climate change is also playing a role in how we're seeing gradually less and less snow over the course of decades, but the exact impact of climate change is unclear. Good news for snow lovers and those who like wintry conditions, a change in the offing for mid to late March and perhaps into April as the overall weather pattern looks to be shifting. As we check out the persistent jet stream flow as a result of that North Atlantic oscillation shift, it's just been back to the north and west. The jet stream has taken every storm basically to the north and west of our local area. That put us on the milder side, and that means lots of the precipitation that fell, of course, was in the form of rain, and this jet stream really hasn't budged much since Christmas. And where it's been cold for several weeks and months, and that's allowed a significant snow to accumulate. Not much in the eastern third of the United States, but in the center portion of the nation and back to the west, it's been a completely different story. Check this out. Flagstaff, Arizona, 130 inches of snow so far this season. This is through March 1st, 61 inches of snow above average. All across the western U.S., we've seen the national headlines. In California, copious amounts of snow and rain. Casper, Wyoming, 86 inches of snow, over 4 feet above seasonal average. And these other cities, Minneapolis, Salt Lake City, Goodland, Kansas, even Portland, Oregon, almost 12 inches of snow, 7 inches above seasonal average, all as a result of that prevalent jet stream that really hasn't moved much, and it's kept the storm track to our west, keeping cold temperatures across the central and western U.S. As a contrast, very little snow has been falling in the eastern United States. Check out these numbers. D.C., Philadelphia, New York City, snowfall amounts of 2 inches or less. Boston, Massachusetts, and Portland, Maine, not much snow here either. amounts quite a bit below seasonal average. Portland, Maine, 10 inches below seasonal average. Even areas that typically see lots of snow, like Syracuse, New York, 4 feet of snow. That's it so far. Typically, they're over 100 inches of snow over the course of a season. So definitely, we're not the only ones seeing a lack of wintry conditions. It's been pretty prevalent across the eastern United States. Here's a look at February high temperatures, and this is quite impressive, actually. As we look at these numbers, highs in the 40s, 50s, and 60s for much of the month of February. Only 3 days in February had below average high temperatures. 25 days in the month of February had temperatures that were above seasonal average. So when you look at highs in the 40s, 50s, and 60s, it's no wonder that we really weren't able to accumulate much of any snow. And in fact, this February was rather notable, the second warmest February on record, but we only had a trace of snow here at our TV station. Over the past several decades, we haven't had any other Februaries with no measurable snow in Lima. So certainly very unusual conditions this time of year. And again, there are some signs that that could be changing as we're going forward, of course, as we head into the second half of March. December, January, February, all 3 months of meteorological winter this year above average. December was close to average. Of course, we had that winter storm just before Christmas with temperatures below zero. After that, not much of a winter. 8.5 degrees above average in January, 8.2 degrees above average in February, both January and February, the second warmest on record. This compares to last winter when we actually did have cold temperatures for January and February, below average temperatures. And of course, last winter we did have that snowstorm on Groundhog Day, which brought 8 inches of accumulation to Lima. In terms of snowfall, typically we're good for about 24 to 30 inches. There's incomplete snowfall records within the city of Lima, but across our region, generally anywhere from between 24 to 30 inches of snow accumulates in a typical winter. Look at that. 2013, 2014, 51 inches of snow accumulated, and that was the year, of course, where we had that intrusion of the polar vortex with much below average temperatures and several rounds of snow. In recent years, our amounts have been less, and of course, this year, really not much to speak of. Through March 1st, here at the TV station, only 8.7 inches of snow. Tough to see how we reach that 24 to 30 inch range, although we will likely make up some ground through the second part of the month of March as our weather pattern does look to trend colder in the coming weeks. And these subtle changes, we talked about climate change, that does add up over time. Check out these numbers. Between the last 30 years, December 1991 to 2020, our typical December temperature, the average 31.5 degrees, but over the last 10 years, we've been 2 degrees above that. So quite a drastic change in the last 10 years, warmer conditions for December. And we've noticed this pattern. Our winters have been happening later, and that looks as though that pattern may continue in the coming years. January and February temperatures slightly above the 30-year average in the last 10 years. February only barely above, but subtle changes make a difference. Every little bit of a temperature change means fewer and fewer days where we have that opportunity to rack up snow accumulation. So definitely an unusual winter. It's been warm. It's been relatively snowless. That's the way things have been. Coming up, meteorologist Nathan Kitchens is going to talk about what we can expect in the coming weeks and months with the seasonal forecast. That's coming up next.
Chief Meteorologist Adam Mussett discussed our historically mild winter season, and a product of all that warm weather has been a number of windy days, which I'm sure you have noticed. So we're going to discuss why it has been so windy around here, and we're going to take a look ahead as far as what the spring season may hold for us here weather-wise. So first off, the number of windy days. In fact, we've had double the amount of days with wind gusts exceeding 40 miles per hour when you compare it to last year at this point in the year. So yes, we have seen a lot of wind. But why is that? So first off, I want to discuss what causes wind in the first place. And basically, you just need to know that wind is driven by differences in air pressure. So the air is always trying to reach a state of balance or equilibrium, and it's the same as true on a global scale. So we have areas of high pressure, and then we have areas of low pressure, and the air always flows from high to low. So an example of that is if I blow up a balloon, and then I let go of it, you notice how that balloon flies away because you get all that high pressure inside of it. And while the outside of the balloon, you have relatively lower pressure. So the air goes from higher to lower pressure. And it's the same thing here when it comes to air masses. So we look at air that flows from high to low. When you have a weak difference in pressure, we typically see weaker winds. But when that pressure gradient gets stronger, like in this situation here, we typically see so much stronger wind speeds. And this is what we're looking at when we look at weather maps with these white lines. These are isobars, and that's basically lines of equal pressure. And when they are packed closer together, that represents a tighter pressure gradient, which obviously drives stronger winds because the atmosphere it's trying to reach balance. So when you've got such an imbalance taking place, the wind is that mechanism to fill that void in pressure. So the air goes from high to low to help fill that void. But in the process, we get some very strong winds, as we have seen a lot of this winter. And the winter time typically is our windier time of the year. And the reason why is the jet stream.
We've had temperature and pressure gradients across the area where we've got tight packing and drastic changes in temperature and pressure across the area, which do allow for stronger winds in these cases. And especially in some of these instances, we've had a little bit more in the way of sunshine, and that has allowed for a lot of those winds that are aloft that can be brought back down to the surface.
And in the last segment, Adam Mussett discussed the position of the jet stream and why that did not give us snow, but instead more in the way of rain and thunderstorms. Well, that jet stream position is typically further south in the wintertime, and it's typically stronger as well. So the jet stream is just that ribbon of very strong winds aloft in the atmosphere, and that is typically what we look at as meteorologists as the train tracks for storm systems to move through. So the storm systems are further south over the United States, and that provides a lot of windy weather because we typically see more of that difference in pressure across the area. But as we go forward into the warmer months, say May, June, July, we start to notice the jet stream shifting further north, and that provides warmer weather for the lower 48, but also the jet stream weekends, because part of what drives this strong jet stream is that difference in temperature. So we typically have a lot of warm air south of the jet stream, much colder air to the north, but that difference is not as extreme in the summertime. So the jet stream typically is weaker, so you have weaker systems, they're further north, so we typically see less in the way of windy weather outside of thunderstorms as we go through the summer season. When we look at the imbalance of pressure, we also want to look at the imbalance in temperatures around the globe. So we know that along the equator, if you've ever been down to the Bahamas, we know that they get a lot of warm weather all throughout the year because of the high sun angle. But as you go further north in latitude, closer to the polar regions, it's much, much colder, and we do actually have several months of darkness in the wintertime. So the air is trying to reach a balance. So we have all this heat that builds up and accumulates around the equators. We have all that cold air near the polar regions, and we have the air masses that work to help fill that void, the imbalance, but we also have ocean currents that help kind of counteract that imbalance. So we have warm ocean currents that come from the equator and right up toward the poles, and then likewise we have cold ocean currents that come from the poles down toward the equator. An example of that is here. Look at California. You know, when we talk about California in the weather world, we don't typically talk about hurricanes making landfall there because the water is just simply too cold. That is a stable current, and that's why we typically don't get as much moisture in these areas as well. But we see a warm Gulf Stream here. This is a warm ocean current, and this actually goes all the way into western portions of Europe. So that's why areas like London, for example, why their weather is so moderated and mild in the wintertime, despite them being so far north, they are largely impacted by that warm ocean current. So again, this is just another way that our planet helps to balance out those differences in temperature because we get so much heat at the equator and so much cold air up toward the polar region. So let's talk about wind climatology. What is the windiest time of the year? Well, if you've been watching so far, you probably know by now that the winter time is typically our peak in the windy season here. It still stays very windy through April. Once we get to May, that starts to dwindle down. We get less of those breezy days, and we have the dog days of summer. We don't call it dog days for nothing. It's because we typically see less in the way of windy weather, especially August is typically our least windy month across our area. Now that we talked about why it's been so windy, let's take a look forward as far as what the spring season may hold for us. So when we forecast longer range weather patterns, obviously there are risks involved as far as predicting the outcomes here. What we're going to look at first off is what is normal for our area based on climate. And climate records, we look at 30 years of weather data to come up with that, but we also want to look at signals in the weather pattern that may influence us. For example, we talked about La Nina. Adam talked about how we are in a third year La Nina this past year and how that has influenced our weather. So that is an important driver. And we're also going to look at the past, to predict what may come. So we can look at history, years that had similar conditions in the atmosphere to look at what this spring season might hold. So again, the La Nina that we have been dealing with here for 3 years, it is starting to fade away. So there are other factors, for example, here in the month of March, other factors like the teleconnections that Adam discussed are becoming more dominant, and they are switching positions and allowing for colder air.
Another piece of the pattern here is actually going to be the influence of the polar regions. There is what is called a sudden stratospheric warming, where warmer air pushes into the polar regions and some cold is able to come down. We'll be watching to see if we do get that stratosphere troposphere coupling for that March, middle of March timeframe, and then how long that lasts.
So we look at the rest of March. We are favored at this point to see cooler than normal conditions. Now, the good news is it is March, it's not January, so even below normal is still typically not anything as brutal or extreme as what we would find in the middle of winter. Now, as far as precipitation, some good news in this outlook. The colder air will likely come with a bit of a drop in the amount of moisture. So the higher precipitation total should stay south, and I think we're going to see near normal precipitation locally and even drier conditions as you go up into the Great Lakes. So at least we'll get a bit of a break from the active flooding it appears that we have had over the area lately. Now let's go a little further in time. So we talked about March, but what about the rest of spring? So it still looks like, despite the fading La Nina, we still expect that La Nina type pattern to take hold for us, which is going to lead to a better opportunity for slightly warmer temperatures. Once we get to April, spring will really start to show up around west central Ohio, and we're going to see slightly warmer temperatures, it appears, for the most part through late spring. But this warmer weather, once again, as we saw in February and January, it still looks like that wet weather pattern is going to hold. So I know farmers, those with agriculture interests that are watching this forecast, obviously want to keep a close eye on this, because it does look like it could be a season, if this forecast holds, where we could see some planting delays because of that. So again, we're going to look also at what's normal for us here. We look at averages, how those numbers start to go up from the mid 40s on March 15th. By April 15th, our average high goes up in the lower 60s. And then eventually by May 15th, our average high goes up into the lower 70s. So again, we talked about wind, we talked about what the weather pattern may hold in the upcoming few months, but now we're going to have Connor Prince in the next segment explain basically the technology behind the weather forecast that you see on the air, that finished product every day. We're going to give you more of a behind the scenes look at how we come up with that forecast.
Welcome back, everybody. I am meteorologist Connor Prince, and for our final part of our winter weather segment, I'm going to show you how we forecast winter weather both before and during the winter storm in west central Ohio. But before we get into the scientific details, we need to understand the precipitation types and how it forms based on atmospheric structure. First, we have rain, where we start as snow in the upper levels of the atmosphere where it is cold. Then as it encounters a thick layer of warm air aloft above down to the surface, snow then melts into liquid rain, and then it falls as rain here at the surface in western Ohio. Now we have freezing rain scenario, where we start as snow again in the upper levels where it is cold. Then that snow encounters the warm air aloft and then melts into liquid rain. And then there's this shallow layer of cold air at the surface where there's not enough time for it to freeze back into ice pellets, but it freezes on the surface as ice in freezing rain form. Next, we have sleet, where we start as snow in the upper levels of the atmosphere, encounter a thin air, a layer of warm air aloft, where it then melts into liquid rain. And then we have a thick layer of cold air below freezing on the low levels on the surface, where it freezes back into sleet as on the ground. Finally, we have snow, where it starts out as snow in the upper levels where it's cold all the way to the surface, and that snowflake survives and affects the area in the form of accumulating snow. So now we need to discuss how we get ingredients for a winter storm here in western Ohio. First and foremost, we need a source of cold air from the north. This is usually in the form of a strong area of Canadian high pressure. Then we need a surface boundary, such as a stationary front on the southern edge of that cold air, to help focus air to converge along that boundary for an area of the low pressure to form. Now we need a jet stream and a trough aloft to interact with this boundary. What this does, it then helps pumps the air out of the surface and lowers the pressure. When that happens, we get an area of low pressure to form with a warm front and a cold front, and this is our optimal position in eastern Kentucky for a winter storm here in western Ohio. And notice how that low area now begins to distort the cold air source as well. Now we need a source of moisture. In this case, it's from the Gulf of Mexico. As that low intensifies and that trough interacts with the low, that moisture gets pulled northward. And then once it interacts with the warm front, two things happen with it. The moisture then wraps around the area of low pressure, and then some of that moisture then goes eastward along that warm front. And once this moisture interacts with the cold air here in western Ohio, that's where we get heavy winter precipitation in the form of snow if we're on the northwest side, mixing along that warm front, and then rain south of the warm front and east of the cold front, where that warm and moist air is to our southeast. Now we're going to show you on how a storm track impacts precipitation type and forecasting. So our first scenario is when we're forecasting heavy snow. So notice how the storm track is to our south with the low starting in North Texas. As an area of low pressure moves into Arkansas, we have a swath of snow that approaches from our southwest. As that low pressure then moves into western Tennessee and western Kentucky, we have snow overspreading the area. Then with the low moving into Kentucky, we have enough cold air at the surface and above where the snow stays in the form of snow and moisture where we get accumulating snow. That warm front is to our southeast, so any mixing and rain is off to our southeast because it's too cold here in western Ohio. Then finally, as that low moves off to the northeast, the snow threat ends in this scenario. Now we're on to scenario 2 where we have mixed precipitation in the forecast. And notice how this track is a little bit to the northwest, roughly about 50 to 75 miles, which will make a tremendous difference. So we have an area of low pressure starting in the Texas Panhandle. This low will move into central Oklahoma, and now we have snow just to our southwest. As that low pressure moves off to the northeast, we'll have enough cold air at the surface and aloft where precip will start in the form of snow typically. But as that low then moves into southeastern Missouri, southern Illinois, southern Indiana, the warm front approaches, and then we have warm air aloft that will begin to transition precipitation types in a mixed precipitation form in the form of snow, sleet, freezing rain, and rain. Finally, as that low moves off to the northeast, we have usually enough moisture and cold air left behind where we get a period of snow. And then finally, once it moves off well to the northeast, that snow threat then ends. Now we're going to do scenario 3 of a heavy rain scenario. So notice how this track is well off to our northwest, and even at the initial onset of the storm, the wintry precipitation is still off to our northwest, and with the warm front then surging northward and we're east of that cold front, we are well in the warm sector of the storm, and thus rain will be the precipitation type here into the cold front that moves through. And even beyond the cold front where the colder air surges back, we just don't have enough moisture for snow to occur in this situation. That snow then stays off to our northwest, and then that area of low pressure then moves off to the northeast. Now we're going to show you how we forecast precipitation type with some meteorological tools. So this is a skew T diagram, and notice these red lines here, those are isotherms, which are the lines of temperatures, and the green lines, those are your dew point temperature lines. So now we're going to zoom in here, and where we have these lines close together, that is where we have atmospheric moisture present, and that's needed for both clouds and precipitation to form. Next, these lines where it goes from the bottom left of the screen to the top right, those are your isotherms, which are lines of constant temperature. And notice how the 0 is right here in this blue line. This is your freezing line, and that is a critical point that we need to keep an eye on when we forecast precipitation type. So notice the red line crosses the blue line right about here. This is where the cold air source is below freezing cold air. Then we have that red line that goes all the way to the surface, and it's to the right of that blue line. We have warm air at the surface and low levels that melts the snow into liquid rain, and we experience rain at the surface in western Ohio. Now let's complicate things a little bit with the freezing rain situation. So again, we have our lines close together, which indicates moisture for both clouds and precipitation production across the area. Now we're going to highlight our 0 degree temperature line. We have cold air in the upper levels of the atmosphere. We have a warm air layer of loft above the surface to melt that snow into liquid, and we have just enough shallow cold air at the surface where that liquid precipitation freezes on contact, and that becomes freezing rain and accumulating ice here in western Ohio that usually produces our ice storms. Now we're going to move on to sleet. So once again, our lines are close together, which indicates the presence of moisture across the area for both clouds and precipitation. Next, we're going to go ahead and plot our 0 degree line again, and notice how we have cold air in the upper levels of the atmosphere. The middle levels, we have a shallow air of warm air aloft to melt the snow into liquid form, and we have a thick layer of cold air near the surface that melts that liquid or freezes that liquid form back into sleet. windy, and we experience accumulating sleet. Finally, for forecasting snow, we have moisture denoted again by the lines that are close together. Now we're going to take another step. These are your -12-degree isotherms and your -18-degree isotherms. That is your dendritic growth zone. When you have moisture that overlaps in the zone, that's very favorable for accumulating snow to occur. So once again, we have our 0-degree line here where it is now cold enough from the upper levels of the surface to produce accumulating snow here in western Ohio, and usually our heavy snow. Finally, we're going to discuss how we use radar tools to determine whether we have snow or mixed precipitation occurring. So this is a real radar image during the February 2nd and 3rd, 2022 winter storm. And notice we can't really tell precipitation type in this scenario. As we go off to the right side of the screen, we now have a totally new radar image here. This is called correlation coefficient. Correlation coefficient determines how well the targets are in the atmosphere similar to each other. If they're very similar, we have the high values denoted in the pinks. If they're not similar to each other, we have values shown in the yellows and eventually blues. So where we have this transition zone right here, that is where we have a transition between high values and low values to the southeast. So we have the zone of uniform hydrometeors to the northwest and various hydrometeors to the southeast, and thus this tells me we have snow occurring northwest of this line. We have mixed precipitation occurring along the line from Defiance to Fort Wayne down to Kokomo, and then rain occurring further southeast to that line where we have more warmer air aloft. So overall, it is a very complicated science to determine winter weather forecasting here in western Ohio. So hopefully you guys learned quite a bit of information with this seminar. I'm meteorologist Connor Prince, and thank you guys so much for tuning in. Have a great night.
This has been part one of our series, Weather Changes, What's Next? We've been excited to bring you this information, and we're even more excited to bring you what's coming up over the course of the next week. Be sure to join us next week at this same time, 7:30 p.m. here on NBC Lima, to hear about the preparations and action that can be taken to be safe during our severe thunderstorm and tornadic season, which is going to be coming up over the next several weeks and months. As always, thanks again for joining us, everyone.